A very good morning to all of you. I am Uma Sharma, Assistant Professor in EC Department of Ajay Kumar Garg Engineering College. Today in this video lecture series, we'll cover some complex topic of Unit 1. Actually in this series, I am going to cover some of the complex topics of integrated circuits. So as per AKTU syllabus, this is the first topic of Unit 1, that is the 741 IC op-amp, general operation and amplifier stages. So here we will cover all the stages of 741 IC. So these are the content of my presentation: bias circuit, input stage, then second stage, output stage and the short circuit protection circuit. So basically 741 IC, which is an operational amplifier IC that was manufactured by the Fairchild Corporation, and it is having 24 transistor, 11 resistors and 1 capacitor. So these are the component of this IC, and here you can see that the IC can operate on two supplies. One is plus VCC and second one is the minus VEE. Normally the value of these supply voltages is taken as plus minus 15 volt, but the IC is capable of operating at much lower power voltages such as plus minus 5 volt. So you can see the block diagram of the 741 IC. Each block is having its circuit label, transistor level circuit diagram. So I hope you all are aware with the blocks of the 741 op-amp. It is having basically 3 blocks. One is differential amplifier input stage, then next is a gain stage, and after that there is a output stage. So to support all these stages, we require some biasing by which we can provide power to these blocks. So here you can see in this circuit, this is the actually transistor level diagram of 741 IC. So this is a complex circuit, and here in this unit we have to discuss the analysis of the circuit diagram. So in one go it is very difficult, as we have to analyze 24 transistors along with some resistor and capacitor. So it is better to divide this circuit into different stages. So what I have done here, I have divided this complete circuit diagram into 5 stages. One, that is the stage which is going to provide biasing, that means that is to provide the power to the individual stages. Then the differential amplifier stage, you can see that this is the differential amplifier which consists of transistor Q1 and Q2 along with the Q3, Q4, Q5 and Q6. This can be assumed as the input stage, because you all are aware that the first block of operational amplifier is differential amplifier circuit. So here you can see that this is the input stage. Then again further I have divided it into the gain stage. The as you all are aware, the 741 IC is having very high gain. So to achieve this gain, we require some gain stage. So second stage is known as gain stage, and then finally the output stage. The output stage consists of the power amplifier by which we can take the output. So overall in this circuit these 3 stages are present, and other than that the some transistor like Q11, Q10, 9, 8, 12, Q13, A and B are used for the biasing purpose, and along with these transistors there are some another transistors like Q15, Q21, Q24 and Q22. These transistors are basically to provide the protection to the IC, because in integrated circuit if there is a excess current at the output node, so there is a chance or possibility to damage the IC. So for the protection of excess current, there are some transistor which can be used in the case of excess current. So one by one let's see the each individual stage. So first let's discuss the short circuit protection circuit. As we have seen the internal circuit diagram of the IC, so in that diagram the transistor Q15, Q21, 24 along with the R6, R7, R11 are used for the short circuit protection of the IC. Normally these transistors are off, but whenever there is a excess current, so the transistor are on and they can rob that current and can protect the output transistor from damage. So whenever the large current is achieved, then only these transistors will be on, otherwise these transistors are in off condition. So normally they are off, you can see over here. So the role of short circuit protection circuit is basically to protect the IC from the excess current that may happen whenever the supply voltage is directly connected with the output node. Let's say, suppose this output node is directly connected to this supply node, means there is a excess current, there is a shorting between supply and the output terminal. That means there is excess current, so current will increase, so the voltage across this resistor R6 will also increase, and that will on this transistor Q15. In the previous situation, whenever there is no excess current, this transistor is off. So this transistor will on only when the voltage across this R6 is sufficient enough to on this Q15 transistor. Similarly, whenever this output node is shorted with the minus supply, in that case the transistor Q21 will be on, and that will actually rob some current from here, or in that case this transistor will steal some current from Q20 and Q40, and the excess current problem can be tackled. So this is how the short circuit protection circuit works. So the transistor Q15, Q21, Q24 and Q22, these are the transistors that are responsible for the protection of this IC. Normally they are off, so we can consider that these transistors are having zero current when we are talking about ideal situation. So now come to the next block. As we have already discussed that op-amp is having three main stages. These are input, then gain stage, and then output stage. So we need some circuit to provide biasing to this input stage, biasing of this gain stage, and biasing of this output stage. So that's why we have to understand what is the function of this biasing circuit. So we have divided the complete circuit diagram, which contains 24 transistor, 11 resistor and 1 capacitor, into 5 parts: input, gain and output, then bias circuit and short circuit protection circuit. So here now we can discuss the biasing circuit. So the use of this biasing circuit is to provide the biasing to the different stages. So this is the reference bias current circuit, which consists of Q11 and Q12 transistor, and this circuit is generating a reference current, and this reference current is used to bias the input stage. So basically this is used to bias the input stage. You can see that this terminal is connected with VCC. So the current is going in the resistor R5, which is a 39 kilo ohm resistor, and you have to understand one thing, that this is predefined structure of the 741 IC. So the values of R5, R6, R7, all the resistor is predefined. We cannot change these values. So the value of R5 is 39 kilo ohm. Similarly, the device parameters are also fixed. So for each transistor, there are some specified device parameters. So for the calculation of these currents and voltages, we have to consider these parameters only. So here the current is generated through this branch and can be transferred to the another circuit, and we know that the current can be replicated with the help of a special kind of circuit known as current mirror. So here also we will use the current mirror circuits to replicate the current into different circuits. So if we want to replicate this I reference current to provide biasing to the input stage, then definitely we can use a current mirror, means we can use another transistor over here and we can replicate this I reference to that branch. So here there is the bias circuit for input stage. Then the current which I reference that I am talking about in the previous slide, that is this current, this node is connected with this Q11 transistor. Now you can see the structure of this circuit. This circuit is basically a Bidlar current source, and the use of Bidlar current source is to convert large currents into small currents. So here we are having I reference current which is having some high value in the range of milliamperes. We can convert into microampere. So with the help of this Bidlar current source, we can convert this milliampere current into microampere current, and obviously this the function of this circuit is only to bias the input stage. So again this biasing current is used for the input stage biasing. Here Q8 and Q9, this is another current mirror which is formed by Q8 and Q9, and again this is responsible for biasing of input stage, and you can see that it is a simple structure of simple current mirror. This is the structure of simple current mirror. So if we see the internal diagram of 741 IC, so we have discussed this current mirror, we have discussed this current mirror. So definitely it is connected with input stage, so that is going to bias the input stage. There are some transistor which is forming a current mirror between Q12 and Q13A, Q13 and Q13B. These are the special type of transistor known as bilateral transistor, which is having two terminals, two output terminals. So here the transistor is having two output terminal. One current can be drawn from Q13A and second current can be drawn from the Q13B. But if you see the structure of Q12 and Q13, it is forming a simple current mirror. So this is another current mirror or biasing circuit which is going to bias the second stage. So this Q12 and Q13B is used to bias the second stage, and similarly you can see the transistor like Q18 and Q19. The function of these transistor is also to bias the output stage along with the Q13A. Q13B is biasing second stage, but Q13A is biasing the output stage. So overall in this block diagram we can identify the biasing network which includes Q12, Q11, Q10, Q8, Q9, Q13A, Q13B, and the transistors which are connected between the base of Q14 and Q20 are Q18 and Q19. These transistors are also used to generate the appropriate voltage between these base to base terminals, between the base of Q14 and Q20, or these are also considered as the transistor for biasing. So the biasing part is now completed. Now come to the input stage structure. I have already discussed this point. This is double collector lateral transistor. So the function of this transistor is to bias the two different stages. One is to bias the output stage and another is to bias the second stage, that is Q13B. So this is the internal diagram for input stage, and this input stage diagram is further divided into two parts. One is this differential amplifier. This is differential amplifier, whereas this circuit is considered as load circuit. So if you see the main circuit of the 741 IC, you can identify these transistor Q1, Q2, Q3, Q4, Q5, Q6 and Q7. Here in this slide, I have grounded these two terminals, just representing that we are talking about the DC analysis. As I have already told you, we have to do DC as well as AC analysis for this circuit. So first, with the help of DC analysis, we can set the operating points, then only we can apply the input voltage to amplify it into the certain desired value. So here these terminals are grounded, but obviously we will apply input on these two terminals, and you can see that Q1 and Q2 are forming a differential amplifier, and here the transistor Q3 and Q4 are also used to provide the level shifting in the first stage. So overall the input stage consists Q1 to Q7 transistor, where Q8, Q9 and Q10 we have already seen, these transistors are responsible for the biasing, and Q5, Q6 and Q7 along with the R1, R2, R3 form a load circuit to the input stage. And if you see this diagram, this load circuit looks like a base current compensated current mirror. So it can be solved very easily if you know the base current compensated current mirror. So that will be very easy to calculate these current components if you understand the operation of base current compensated current mirror. So level shifting is required so that the swing of output can be adjusted. Suppose we want the signal in this shape and we are getting this in this shape. So with the help of this level shifting, we can shift the level in downward direction, and similarly we can shift the signal in upward direction. Now come to the second stage. The transistor which are the part of second stage are Q13B, that is for biasing, this Q16 and Q17 with R9 and R8 resistors, and this part we will cover later in this lecture. This is the coupling capacitor which is added in the second stage. So second stage is also known as intermediate stage, and this is composed of Q16, Q17, Q13B and the two resistors. The Q16 you can see that work as emitter follower. This is like emitter follower. The output is taken from this emitter node, and the output transistor which is a Q17 transistor, this is connected in common emitter configuration, but this is connected in the common collector configuration. So you know that the common collector configuration is having gain of 1, but this transistor will provide the additional gain to the circuit. So this is about the second stage, which is also known as the gain stage of the operational amplifier, and also this stage provide the compensation which is known as frequency compensation. There are two types of IC. One is known as internal compensated IC, internal compensated, and second one is the externally compensated. So the IC 741 is internally compensated IC, where we have used a coupling capacitor CC to to nullify the effect of all the parasitic capacitances which are present in the circuit because of the parasitic of different transistors. As you know that the BJT is having its parasitic capacitances which are not required, so that will affect the frequency response of the circuit. So to avoid these undesired fluctuations, we have added a capacitor which is having very small value to the IC that will look after all these parasitic capacitances effects. So second stage is a gain stage, along with it provides some frequency compensation. Now come to the output stage. The output stage consisting of Q14, Q20 transistors. These are the power transistor, and here this network is used to provide to enhance the or to increase the base to base voltage between Q14 and Q20, because these are the output transistor having the area which is greater than all the other transistors which are available in the IC. Generally this area is 3 times. So to increase the base to base voltage, we have added this network Q18 and Q19 to the output stage. Now here we can discuss the output stage configuration. There may be 3 commonly used output amplifiers known as class A amplifier, class B amplifier and class AB amplifier. There is one another category which is class C amplifier, but here we will discuss class A, class B and class AB amplifier. The output stage of 741 uses the class AB amplifier stage. So here we have seen in the circuit diagram of 741 IC, the output stage is class AB amplifier stage. So we can use class A also, but there are some drawbacks of class A amplifier. Similarly, there are some drawbacks of class B amplifier. So let's see the diagram here in this slide. You can see that this is the representation of class A output stage. This stage can be used at the output, but the in this configuration the power dissipation is more, because there is a direct path between supply and the positive supply and negative supply, and all the time whenever this input is applied, the circuit is on. So the power dissipation is more in case of class A amplifier, which is generally a emitter follower structure. So to avoid the power dissipation or to reduce the power dissipation, we can do one thing, that we can add one more transistor with this single stage transistor that we have used in the class A configuration, so that with the help of this we can reduce the power dissipation, because at a time that one transistor is on, another transistor is off. So that will reduce the power dissipation of the complete circuit. So this kind of arrangement is known as class B output stage circuit, where the transistor will be cut off when Vi is 0. Both the transistors are cut off when Vi is 0. So in that case, input is 0, then circuit is switched off. So that means there is a power saving in case of class B configuration. So over class A amplifier, we can prefer class B amplifier, but in that case the signal distortion may be there, because the output signal, whenever the input signal lies in between the threshold voltage of Qn and Qp, in that situation there is a crossover distortion between the input and output, and due to this the output will be looks like the transistor is off in this particular duration. So there is no output, although there is input is available, but this input is not capable to on these transistors. So that's why there is a gap in between two pulses. So this is known as crossover distortion. So to avoid this distortion, we can use the class AB amplifier. This is class AB amplifier output stage, and in this class AB amplifier stage you can see that there are two transistors. This is NMOS, this is PMOS, this is N type of transistor, that is NPN transistor, and this is PNP transistor. So whenever there is a high input, means input signal is high, so the QN will be on. Whenever this input exceed the threshold voltage, if this is 0.5, so whenever this exceed the input voltage 0.5, then this transistor is on, whereas this transistor is off. So output will be due to this transistor. Similarly, for the second type of input, whenever the P transistor is on, then output will be due to the QP transistor. So in that case, the crossover distortion can be reduced if we bias these transistors at very low current. In case of class B amplifier, this was the situation, but whenever the input is in between 0 to 0.5, in that case the output is not present. So that means if we can bias these transistors at the low current, then we can get the output in the situation whenever the input voltage is lies in between the 0 to 0.5. So to bias the transistor like this, we have added Q1 and Q2 transistor in the circuit, and due to these additional transistors, now the circuit is capable to on at very small voltages, because the transistors are biased at the low current. So in this case, the output transistor remain conducting whenever Vi is very small. So actually this was a problem in class B configuration. So here we have added these two additional transistors, but here the crossover distortion is not present. So here you can see that the class here this class AB amplifier is used in the output stage of 741 IC. So overall we have discussed the 741 IC circuit diagram, which is divided into 5 parts. One is short circuit protection circuit. The circuit is responsible for providing protection with the excess current. When we are talking about the biasing circuit, these circuits are responsible to bias the different stages like input stage, gain stage and the output stage. And biasing circuits are consisting of different current mirrors like simple current mirrors and Widlar current source. Then we have discussed the input stage. So input stage basically a differential amplifier stage, and with the help of differential amplifier we can reduce the effect of noise. This is the beauty of the operational amplifier, where when we apply the input at positive as well as negative terminals, the noise can be eliminated, because the effect of noise will be on both the terminals. So we can nullify the noise effect. To shift the level or to get the full swing, we have added one level shifting stage in the along with the differential amplifier, which is formed using the Q3 and Q4 transistor. And to differential amplifier stage, there is a load stage which consists of Q5 to Q7 transistor. Then we have discussed about the second stage. So the circuit is the second stage consists of Q16 and Q17 transistor, and that provide the maximum gain to this operational amplifier stage. In the last stage we have used the class AB amplifier, and this class AB amplifier is the best configuration to be used as output stage. So overall this 741 IC is divided into 5 subsections, and we have noticed one thing. There is one capacitor which is connected at the output stage, and this capacitor is responsible for the frequency compensation. With the help of this capacitor, we can nullify the effect of parasitic capacitances. So once we have studied the different stages, then we have to analyze these stages for DC configuration as well as for the small signal. We have to do the analysis in DC domain as well as the AC domain. So whenever we are talking about the DC analysis, that means here the input is 0 and we have to set the operating point of each transistor. Like if we want to operate Q1, Q2 transistor in the active region, so we have to bias the Q1 and Q2 accordingly, then only we can apply input to the circuit. So biasing is something like fuel to your car. So we require biasing to the each and every transistor of the circuit. So in DC analysis, by providing biasing, we can set the operating points. So one by one in this unit, you have to do DC analysis of each stage, like input, intermediate and the output stage. Then we have to do the small signal analysis of this 741 IC, which we have divided into 5 parts. So for small signal analysis, definitely for the biased circuit, we don't need to do some AC analysis, because it is the use of biasing circuit is just to provide the current to the different stages, and here in biasing means we are talking about DC only. So whenever we can do the AC analysis of the circuit, and for AC analysis, for this AC analysis, for the AC analysis, we have to apply input to the circuit, and with that input we have to see the output and amplification factors. So in case of AC analysis, we will do one thing, that we will make all the DC voltage sources at the ground potential, and then we will apply the AC input to the circuit, and with the help of hybrid pi model, we can do AC analysis of these stages one by one. So here the total content of this unit is like this. First we have studied the different stages of the 741 IC, then we will study the DC analysis of these all 5 stages, then we have to do the AC analysis, then that is for input stage, second stage and the output stage. So this is all from my side. Thank you so much.